Hey, hello. This is an official school number. I think you have the wrong number, buddy. Yeah, from True Capital asked me about my mortgage insurance. His name was Justin, though, same as me. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good to hear. Yeah, the heat is driving people away. I think that's the answer. Okay, so plan for today. We're going to finish up our open foam activity. We're basically right at the end. So we already ran the simulation. So the only thing left to do is just to look at the results, which I think is the exciting part. So it's a little bummer we didn't get to that last time because last time we kind of spent just 75 minutes staring at a Linux terminal. So you actually get to see the fruits of your labor today, so which is really cool. So that won't take the whole time. So I think that'll maybe just take the first 20 or 30 minutes. And then after that, we need to get back to lecturing because it's been a while since we've had a lecture. So today we're going to start a discussion of how to actually discretize the Navier-Stokes equations. So everything up till this point we've been working on. Essentially, we've been working on just the heat equation, just a general conservation equation with just diffusion and convection. So we'll actually see how that's applied to Navier-Stokes, which you're going to see is a much more challenging equation to solve. Okay. All right. So that's the plan for today. Remember, this activity is due a week from today. So after today, you should have everything that you need. So one thing I'm gonna talk about too today is that there are some things that you still need to do. It's not that you just kind of watch what I'm doing and that's the activity. There are several problems for you to do at the end. And so we'll talk about kind of what that entails later today as well. Okay. Any questions I can answer before we get started for today? Okay. All right. So before we begin, actually, would you mind turning off the light just so it's a little easier to kind of see in here? Thank you. Okay. So before we begin, let's just kind of summarize the process that we need to take to run an OpenFOAM simulation. Okay. So if you remember from Monday, running an OpenFOAM simulation is probably unlike anything you've done in terms of engineering software. And you guys have used a lot of engineering software up until this point. SolidWorks, MATLAB, ANSYS, CATIA, right? OpenFOAM is not like any of those. In some sense, OpenFOAM is very efficient because it doesn't need to use any kind of memory or any kind of things to show you a front-end graphical user interface. And so it's all done through command line and text files. Um, and so, OpenFOAM is a very efficient program in that sense. One of the big things that takes up a lot of space for these kind of more bulky engineering programs like SolidWorks, believe it or not, is the front end graphical user interface, because that is not easy to program and that does take up a lot of space. So OpenFOAM kind of cuts out all that fluff, you could say, and just gets to the meat of what we expect, which is just running CFD simulations. But it also makes things a little bit difficult to use because it's not exactly user friendly. Okay. Okay, so to run a case from scratch, this is generally what I recommend, especially when you're first starting out with OpenFOAM. Remember, OpenFOAM has a long kind of suite of different tutorials that you can run from, right? So remember, the first thing that we did was we copied from these tutorials case folders. So remember, we did CP -R, and we use the environmental variable foam tutorials. Okay. Right? And you can see that there are quite a few tutorials here for us to choose from. And so generally, if you just want to run a pure CFD simulation, you're going to go into the folder called incompressible fluid, right? So we're not really interested in multi-region, multi-phase flow, heat transfer simulations. We're just looking at fluid, okay? So we're going to go inside the incompressible fluid folder. Okay. And you can see inside here, there's a bunch of case studies or tutorials that you can run, okay? So when you're first starting out in OpenFOAM, and I'm in this category as well because I was telling someone yesterday, I think I've told everyone in this class that I'm learning OpenFOAM right alongside you guys. I do have a lot of CFD experience, just not in OpenFOAM. Generally, what I recommend is to start from one of the templates or from one of the tutorials that we have here, and then modify the input files to fit your particular case. Okay. So for this first activity, there's not much modifying that we had to do just because we're basically just running one of the tutorials just right out of the box, which is the cavity case. Okay. And so you would copy the folder or the case folder of whatever you want to use as a template into your current directory. Okay. So I already did this, so I'm not going to run the command again, but and you guys all did that as well, right? Right. And then if you go inside that case folder, okay, you'll see that there are several folders for you to go into to define your case, right? So last time we talked about the contents of all three of these folders, right? So the folder that you're probably going to spend the most time in is the systems folder. Okay? And in particular, there is one file here that you're going to use to define most of your geometry and mesh, which is the block mesh dictionary file here, right? So let's just do a quick summary of this file here because that's the one where you're going to spend the most time in, right? So let's open it up in a text editor. Okay. Right, and so you can see that inside this file there is sections for you to define your geometry. And so in this particular case, we define our geometry in terms of all the different points that define the all the different vertices of your geometry, right? So just to kind of remind you, for this particular case, we are working in a box. And so all of the vertices of the box are given by these numbers here. And those coordinates are given by this list right here. Okay. Next, you define inside here, you define how fine you want your mesh to be. And so here we're defining our mesh to be 20 by 20. So that's 20 cells in the X direction, 20 cells in the Y direction. Okay. With no grading, we're essentially saying we have a uniform mesh. Okay. Next, we define all the different surfaces. This is just so that we can apply boundary conditions, right? And so we define the moving wall, and so that's defined by the vertices 3, 7, 6, 2, right? So you can go back to our figure here that is defined up here. Okay. We define the fixed wall similarly and the front and back as well. Okay. Now for this case, this geometry was obviously made for you. This was already done. But if you were to run a simulation on your own, right? First thing you would probably do is you would either add to this list of vertices or change them in order to fit the geometry that you want to run a simulation on. Okay. Right. So that's what we're going to do in activity two. So activity two, we're going to run on a more complicated geometry. We're going to simulate flow in a branching path. That's kind of my plan for the for activity two. I'm still kind of drafting it up at this point. Okay. So what you're going to see is that during that activity, we're going to be making changes to this file right here and adding vertices here to adjust for that. Okay. Okay. And in fact, this is actually a part that you're actually going to come back and modify for the for activity one as well. And so I think the last problem that you're going to do in activity one is adjust the geometry. You're not going to add any points. You're just going to adjust the points there in order to change the dimensions of the geometry. Okay. Okay, so that's the block mesh dictionary file. So this one, you're almost always going to pay this one a visit, just because there's just a lot of important stuff in this file here. Okay. Okay, so let's go ahead and exit out of this file. Okay. Next file that we looked into was control dictionary, right? Normally, this is a file that you would also spend a lot of time in adjusting the time stepping parameters. For now, we're not really going to change anything because we haven't discussed time stepping just yet. That's going to be our first topic after the spring break. But once we kind of go through that, then this part will make a bit more sense. Okay? But for now, most of your attention is going to be on block mesh dictionary, right? FV schemes, FV solutions, there are important settings there. They're just kind of beyond what we can discuss in this class. So for the most part, you're going to keep those the same. Okay. For the next folder that we looked at was the constants folder. So constants, this was basically where we can define our viscosity, right? So we look inside the file called physical properties, right? This allows us to define the kinematic viscosity of our fluid. Okay. And then we can look under momentum transport as well. And here you can change the turbulence model and specify different types of turbulence here, which is relevant if you're doing turbulent flow. Okay. Okay. And so the last thing that we covered before we left on Monday was how to specify the boundary conditions. Okay. So to specify the boundary conditions, you're going to go inside this folder, the zeros folder, and we're going to be looking at two specific files. So we're going to look at U, okay, and P. So U here is our velocity. So that's where you can apply your velocity boundary conditions, and P, that is your pressure file where you can supply your pressure boundary conditions. Okay. So if you look inside the U file, right, you can see here that we've applied three different types of boundary conditions. So on the one hand, we applied a moving wall boundary condition, which is saying that the boundary condition on the moving wall, which again is the top boundary of our domain, has a uniform velocity of 1, comma 0, comma 0. So that is a velocity of 1 meter per second in the x direction. Okay. All right, and then for the fixed walls, so that is the two lateral surfaces and the bottom surface of our box. We're applying a no-slip boundary condition, which defines our velocity to be 0. Okay. And then the front and back surfaces, we apply a special empty type boundary condition, because remember, this is technically a 2D simulation. Okay. And then for the pressure, we didn't really change anything here. All of our boundary conditions are on velocity, but if you did have a pressure type boundary condition, you would do so here. Okay. So in activity 2, we'll discuss kind of what it means to set a pressure type boundary condition and how that affects your solution. Okay. But for now, we're just going to leave that alone. Okay. So So that's essentially what it means to set up an OpenFOAM simulation. So, you're not really clicking around in a user interface. You're literally just modifying these text files to fit your. Okay. So after you've set all your text files, running an OpenFOAM simulation is very straightforward. And so the first thing you need to do is we need to generate our mesh. Okay. So you guys all did this last time, but I'm just going to do it again, just kind of illustrate for you. So to generate your mesh, you're going to run a command from your command line called block mesh. Okay, so you just type block mesh, right? And you want to make sure that you are inside your case folder. So you make sure you're not inside one of the subfolders here. You're not inside 0 or constant or system. You're in the folder where you can see all 3 of these folders here. Okay, so we're going to go block mesh. Okay. So this mesh runs extremely quickly just because this is a fairly small case. And so you can see here we have 400 cells in total. So that's 20 cells in the X direction, 20 cells in the Y direction. You multiply those together, that gives you the total number of cells. Okay. And so if your mesh runs correctly, then you should get this result here, no problem. Okay. And then to actually run your simulation, it's another very simple command that you would run. And so you would type in the command called foam run. Okay. Okay. And so again, you guys have probably already done this if you were kind of following along on Monday, but I did clear my case just to kind of illustrate this whole thing again. Okay, so let's go ahead and hit enter, right? And so you're going to feel like you're in the matrix for a second, right? And then all of this output gets there. Okay. And then if you reach the point down here where you see the word end and there's nothing alarming here, so if there's any kind of error, usually it'll say at some point here it tries to make it pretty obvious. But if you just see a bunch of just white text here with no error, that means your simulation was good. Okay. And remember, one thing you always want to check when you run a CFD simulation is you want to check the value of the Courant number. Okay, so the Courant number is a non-dimensional number, just like we mentioned last time, that measures the stability of your simulation. Generally, you want your Courant number to be less than 1. Okay. And so in this case, it is less than 1, so we are in a stable situation. If you have a situation where your Courant number is greater than 1, then usually what you need to do is you need to reduce. So if greater than 1, right? Reduce time step size. Okay. And so we'll actually talk about that kind of after this. Okay. Because the location where you change the time step size, remember, is in the file called control dict. Okay. Okay. We'll talk about that in a second. But first, let's look at the results. But before we get to the results, are there any questions? Yes. It's not. So Courant number is a function of the velocity. It's a function of the grid size and a function of the time step size, roughly. And so usually if your Courant number is too big, that means usually your velocity is too high. And so if you have a situation where you can lower the velocity, then that'll help your Courant number. But most times velocity is not something that you have control over because that's a function of your boundary conditions, and you want to set the boundary conditions so that they're accurate to your real life. So most of the time, the time step size is the best way to do it. The other way to lower Courant number is actually to coarsen the mesh. It's a little bit kind of counterintuitive. And so if you coarsen the mesh, that'll actually lower your Courant number as well. Yeah. All right. Any other questions before we start to look at the results? Okay. All right. So to open the results, thankfully for the results, there is another program within OpenFOAM for you to view the results from a graphical interface. And so the program that we're going to launch is called PairView. And so PairView is kind of the de facto default program that everyone uses to view their CFD results, except for ANSYS for some reason. ANSYS has their own weird kind of fluent thing where you view the results. They don't want to play. They don't want to play on the same team as everyone else. And so to launch PairView, there's actually an OpenFOAM specific implementation of PairView that gets installed with OpenFOAM. So you're going to run a command called parafoam. Okay, right. So the F is capitalized, so it's parafoam, all is one word, right? So go ahead and hit enter, and that's actually going to launch another program in your computer to view your results. Okay, so mine launches pretty quickly just because I've run PairView on this computer a lot, but yours might take a little bit more time. Okay. By the way, I apologize. I don't know if there's a way to zoom in on the interface here. So, you guys will just have to squint, I guess, to see what's going on. But I'll do my best to kind of highlight things with the arrow here. Okay. Okay. So is everyone following along? Everyone able to open PairView? Everyone see this? Okay. Okay, so right now what you're seeing first is a blank screen. So the first thing you have to do is load your results. Okay. So it's already kind of preloaded here, right? So you can see that we have the result called cavity.openfoam, but we need to actually import it in. So to import it in, there is a green button on the left-hand side of the screen called apply. So go ahead and hit that. Okay. So after doing so, you should see a block here, which is your geometry. Okay. Okay. So there are several different results that we can look at. We can look at the velocities and the pressures. But first, let's actually look at our mesh because we haven't actually taken a look at that yet. Okay. So to view your mesh, I think the easiest way to do so is first just to make sure that you're viewing your geometry as kind of a solid color here. And we're going to go to this drop-down menu right here. Okay. So by default, PairView is going to show you your results as just the surface contours, right? But if you want to see the mesh, you can actually change this. Instead of viewing the surface, you're going to view the surface with edges. And so the edges are going to be the edges of your mesh. Okay. Okay, so we do that. We switch this to surface with edges, and now we see our mesh here, right? So you can see here that we have mesh elements, right, or mesh cells. And so if you count it in the x direction, there should be 20. You count it in the y direction, there should be 20. And that shows us all of our results just like that. Okay. Okay. All right, so that's a good way to kind of view your mesh. And by the way, you don't have to wait until you run the simulation to view the mesh. You can actually call Parafoam from your terminal after you run block mesh if you want to see your mesh before you actually run the simulation. Okay. Okay, so let's actually now look at our velocities and let's look at our pressures. Okay. Okay, so to view your results, we need to kind of change the field on which we're looking at. And so the way we do that is if you go to this section of PairView right here, there is a drop-down menu where which you can use to view different results from your simulation, right? So right now it's displaying a result called VTK box block colors, and so it'll show you different colors for the different blocks. For our case, we just have one block, so it's all just one color. But if you want to view the velocity, right, you can go to this menu, and you can click one of these entries here that has U. Okay. And so you might be asking, what's the difference between the first U and the second U, right? So the first U here, you can see that the next to it is a little dot. And so that tells you that that velocity is being shown to you that's at all the grid points in your mesh. Or you can click on the U with the little box next to it, which is going to show you the cell center values of the velocity. So all the velocities that are defined at the cell centers, okay? Usually, in most cases, it doesn't really matter all too much which one you pick. What you're going to see is that they look actually very similar. Okay. So you can see we can look at the cell center U or the nodal U, right? So with the nodal values, you can see the boundary conditions a little bit better. So you can see here that our top surface here, let me bring the color bar over. Our top surface here has a velocity magnitude of 1 meter per second, right? That's exactly as we prescribed it. But actually for me, generally I'd like to see the cell center values of U because that tends to be a little bit more. Okay. Okay. All right, and then you can also view the pressure too, but the pressure in this case is actually not that interesting. So we're actually just going to focus mostly on the velocity. Okay. Okay. All right. So what you're looking at here, it looks like just a blue square, right? And if you look at the color bar here, blue is actually zero velocity. So you might be wondering, right? So we went through all this trouble to run this simulation, and we're getting zero velocity everywhere. That doesn't seem right, right? Well, that's because we're only looking at the initial conditions right now, right? And so if you want to view the conditions at steady state, we need to move the time bar up here, okay? Remember, if you think back to last on Monday, right, when we set the control dictionary, we basically specified the simulation to run for 10 seconds, okay? And right now we're viewing the result at 0 seconds. And so to view the results at the end, right? So this play bar here kind of has kind of has the same kind of intuition that you might have for a play bar on your music app, right? And so let's skip all the way to the end because since we're doing a steady state simulation, the only thing that really matters is just whatever's happening at the end. So let's go ahead and click on this arrow right here, right? So that's the arrow that's pointing to the right. That's right next to the refresh sign. Okay. Right. And so now we actually have some results here, right? It doesn't look that impressive. I know it doesn't look that cool, but trust me that there is some velocity here. Okay. All right. So was everyone able to kind of get this result here with with kind of the little kind of cloudy looking velocity field on the pair view? Good. Okay. All right. So let's actually see what's going on here. So, right now we're not really seeing anything because if you look at the color bar here, right? The color bar is scaled based on the maximum velocity in your simulation and the minimum velocity in the simulation. Okay. Remember, the maximum velocity in this case is actually specified on the top row here, which is we're specifying that entire surface there to move to the right, the velocity of 1 meter per second. Okay. Now, your fluid is moving everywhere else in the domain. It's just not moving nearly as fast as the top boundary because that's kind of what the maximum speed is. Okay. So let's adjust the color bar just so that we can actually see things here. So to adjust the color bar, you're going to click on this button in the interface right here. Okay. So what that button's going to do is that lets you set a custom range for the color bar. And so you can see right now that it's set to 0 and 1. So let's change this from 0 to 1. Let's change it to 0.3. Okay. Right. So that way the maximum color or the reddest color that we see is going to correspond to 0.3 meters per second. Okay. So go ahead and hit rescale. Right. And now we see a little bit more interesting results here. We see kind of velocities that are, not just little white speckles. Okay. Right. Question. Yes. I did 0 to 0.3. Yeah. Yeah. But you can play around with that number too. So depending on what that number is, you'll see different. The color contours will be different. Right. So it's important to remember that, when we're changing this range, we're not changing the results, right? So the results are already there. So we already ran the simulation. We're just changing how we display them, right? And oftentimes, you need to play around with that range a little bit just to make sure the results look a little bit nicer. Okay. Okay. Another thing you can do, so this is just purely optional. But for me, I like to kind of change this color. For some reason, the default color in pair view, there's a good reason for it. There's this color scheme that they pick here is actually very visible for people of all different ranges, color blindness and everything like that. But if you're like me, you're like an RGB kid that likes just bright flashing colors, you can change that. And so to change the color scheme here, you can click on this button right here. Okay. And so that's going to bring up this menu here on the right. And then on the right here, there's kind of a small button here with a heart, okay, that you can click. And then you can change your color scheme for the results to anything that's here. So you can change it to this kind of, kind of Mountain Dew type, green, dark blue kind of color here. You can go to this kind of like icy hot color scheme here. You can go to the rainbow one. This is my personal favorite. I like the rainbow just because I like bright colors. Or you can do turbo, which I guess is the same as rainbow, but with more contrast. And so, if you're truly kind of like to see those colors. So this is purely optional, by the way. The color is just your own personal preference. But I kind of like just the rainbow color there. So, but if you're fine with the default color scheme, you know, which is this one right here, that's just cool to warm, then that's perfectly fine too. So, okay, all right. So that is just the basics of kind of how to display the results in pair view. Okay, so to kind of summarize, first thing we did was we changed the viewable field here. So we changed this to view the velocity u. You can also use this to view pressure. Next thing we did was we changed the time so that we made sure that we were at the steady state. So we maxed this out, right? And then the last thing we did is we adjusted the range so that we can see the differences in color a little bit better. Okay, so this is the basics of kind of what you're going to do for every CFD simulation. This is how you're going to view your results. So when you guys are kind of preparing your OpenFOAM activity reports, when you guys are doing your final project, these types of figures are going to be in your report. So it's good to kind of know how to display these and how to kind of manipulate things to get the display or contours that you want to see. Okay. Okay. Any questions on this? Okay. All right. So that's the color contours. Right. So color contours are great. It's a very quick and easy way to kind of show your results, but it's not a true representation of kind of what we're seeing here because the what we're viewing here is the velocity. But actually, if you look at the color bar, right, what we're viewing actually is the velocity magnitude. We're not actually looking at the velocity vectors, right? Because remember, velocity not only has magnitude, but it also has direction as well. Okay. So to view the velocity directions, we're going to make use of something called a filter, right? So ParaView has all these different filters that you can use to kind of display your results in a different way, right? So the first filter that I'm going to teach you is called the glyph filter, okay? So the glyph filter is given by this kind of globe-looking button here in the interface. So let's go and click on that, right? And what the glyph filter is going to do is that it's going to basically populate your domain here with a bunch of arrows, and those arrows there are going to show the directions of the velocity, okay? Okay, so after you click on that glyph there, right, you're going to see first of all that it's going to create kind of a glyph object here in your pipeline browser, right? So that shows you that you're making the glyph. And then the settings for that glyph are going to be shown here in the bottom left-hand corner of the screen, okay? So if you've ever used any kind of engineering software, they all kind of have used the same kind of convention. ANSYS is this way, SolidWorks I know is this way, right? Generally, when you need to specify settings for a particular part, that usually happens on the bottom left. So ParaView is kind of that same thing. Okay. Okay. So what we want to show here is we want to show the velocity of vectors. And so the way we do that is that we are going to be setting the orientation of the arrows according to our velocity vectors here, right? So right now it's nothing just because we haven't selected anything. And so let's go ahead and click this, right? And it's going to give you an option of either the velocity at the grid points or the velocity that's at the cell centers. Okay. Again, it doesn't really matter which one you pick. It's going to be the same velocity, but I prefer the cell center velocity. So let's go ahead and do that. Okay. And then let's go ahead and hit apply. Right. And so after you hit apply, you're going to see that we have these vectors here, and it looks kind of strange, right? And so what's actually happening is that it is actually showing you all the velocity vectors on the inside, but our geometry here is kind of getting in the way. Okay. So to actually kind of display our vectors inside, we need to adjust the opacity of our geometry here, just so we can see on the inside. Okay. So to adjust the kind of the opacity of our geometry here, we're going to go back to our pipeline browser, click on cavity.openfoam, okay? And then in the bottom left-hand side of the screen, you may have to scroll down for this, right? And so if you scroll down on that list there should be a setting here for opacity, okay? So right now it's set to 1, which is no see-through at all. So our geometry here is viewed just as a solid. But if we change this, right? It doesn't really matter what you change it to. You just have to change it to something less than 1. So I'm going to go ahead and change it to 0.3. Okay. Right. And so that lets us kind of see through our geometry. And you can see by doing that, we've displayed kind of the velocity vectors on the inside. So you can see here that we have this kind of really kind of interesting kind of spinning vortex flow, where the flow is kind of, the flow is being influenced by this top boundary here, It's moving to the right and hits the wall, and then it comes down, and then eventually kind of forms this kind of really beautiful looking spiral within the cavity. Okay. All right. Question, yes. Yeah. So those green arrows are interesting because they are velocity vectors, but they're velocity vectors that are defined on the boundaries. And so remember we defined no slip on this surface here. So no slip basically means zero velocity on those boundaries. So you would think that for the boundaries there we'd have no arrow, but actually right now we're displaying all of the arrows at the same length. So basically we're just showing the direction. Um, and so even though it's zero, technically there has to be a default direction in order to display it. And so the default direction is actually going to the right. So that's kind of what you're seeing. Yeah. Mhm. Yeah. And the fact that it's zero, it's kind of showing you that by showing it as green. So it's saying that, there's kind of a weird value here. So we're gonna show it anyway, but it is something that's not truly defined.
This is awesome to show the magnitude via the arrows.
It is. Yes. So that's the next thing actually we're going to do. So actually, if you go back to your glyph filter here, right? Right, so you go back and left click on glyph once again, right? And so you can see here that underneath orientation, there is another setting here for scale, okay? And so with the scale option there, you can scale the size of the arrows based on the magnitude of the velocity vector, right? Because right now there's no scale. All the velocity vectors, all the arrows are the same size. But generally you want to display, the way you want to display it is, larger velocity magnitudes should have a bigger arrow because they're big, right? And so to scale it, you're going to go ahead and click in here, and then you're going to click from this drop-down menu based on the quantity that you want to scale it by. Okay. So since we want to scale it based on velocity, so go ahead and click on that. Okay. Okay. So after you do that, go ahead and hit apply. Right. And it's going to look really weird because it's going to look like most of your arrows disappear, right? But the only reason for that is because remember the top surface here has the highest velocity. And so it kind of scales everything based off that. So compared to that, everything else is actually really small, right? And so if you want to kind of show everything on the interior, you do have to adjust the scaling factor right here, right? So by default, it's 0.01, right? So you can adjust this, and so for some reason it kind of blows up to this number here. So I forget exactly what I did here, but let's try 0.1. Okay. Right? And so if you change that scale to 0.1, you can see that the size of the arrows kind of adjusts based on the velocity magnitude. So first of all, you can see here that on the top surface, these get kind of, cartoonishly large because those are the biggest ones. So you kind of just have to ignore that, unfortunately. But then everything else on the interior here, you can see it's scaled based on their magnitude. So, near the middle of the domain here, our velocity is almost zero, right? And you can see that the arrows on the boundaries also kind of disappear just because we have the no slip boundary condition, right? And our velocity kind of has higher magnitudes kind of near the edges of our domain here. Okay. All right. And so another thing you can do, you can see right now the arrows all have the same color. So if you want them colored by the velocity magnitude as well, you can kind of go back up to this entry up here. Okay. Right. So whenever you create a new object in the pipeline browser, it kind of changes back to the default colors and default kind of field here. So let's go ahead and change this to U as well. Okay. And then let's go ahead and adjust the range here. So let's go ahead and, oops, this one here. So I'm going to change this to 0.3. Okay. Right. And then let's go ahead and change the colors. Let's do our RGB. Okay. Right. So now we have kind of a nice color contour of our results here, right? Where our velocity glyphs kind of illustrate the magnitude and direction of the velocity within the interior. Okay. All right. Any questions on this? Okay. All right. So let me just double check to make sure. So that's the main thing I wanted to show you with the post processing, just at least how to display the color contours and display the glyphs. Let me just check to make sure that I did get everything here. And by the way, everything I talked about here is outlined in this document as well. So, if you want to kind of do this at home, some of you may have already done this, but, you can kind of follow along here as well. Okay. All right, color contours, glyphs. Okay, yeah, so that's it. So we'll talk more about different post-processing tools as we kind of do the different activities. But I think that's kind of good for the basics, right? So that kind of shows you how to do the color contours and the glyphs, which are going to be part of kind of most results that we have. Okay. Okay. All right. So when you're done with pair view, you can just close it out. So there, you go to the pair view window, you just click on the X there, right? Right. So that kind of returns you back to your terminal here. Okay. So one more thing to kind of show you before we kind of close things up, right? Right. So after you run your case, right? So we're back in the terminal here. So after we ran foam run, you can see that multiple other folders were created here, right? Because remember, before we ran the simulation, we only had three folders. We had the system folder, the constant folder, and the zero folder, right? But after we ran our simulation, more of these folders kind of showed up, right? We have 0.5, 1, 1.5, 2, 2.5, 3, 3.5, so on and so forth, okay? So each of those folders has the results of your CFD simulation at different times that you define. Okay. So in this particular case, we saved our results every 0.5 seconds, and so that's why we have all these here. Okay. But that's generally what OpenFOAM is going to do. So that every time you ask OpenFOAM to save your results, it's going to do so by saving a new folder. Okay. And just to remind you, the way that you specify how often to save is you go into the control dictionary file here. Okay. Okay. And so basically you can say this right here. So the way that you define how often to save is you define this right interval, and that's going to be multiplied by your delta t. So this is saying that we're writing our results every 100 time steps. And if our time step size is 0.005, that means we're writing our results every 0.5 seconds. Okay. Okay. All right. So last thing I'm going to show you here before we kind of talk about the rest of the activity is, let's say that, you ran your simulation and you're kind of been doing a bunch of stuff, but, you kind of want to just reset everything and start from scratch. Okay. So to reset everything, right? So let's say that you want to just delete all of your simulation results and just return you back to the beginning. There is a special command for it. Okay. So the command to delete your results and start over is foam, uppercase C, clean, uppercase C, case. Okay. And so if you run this command here, it's going to delete all of your results and return you to kind of your base state, which is the zero, the system, and the constant folder. Okay. Okay, so I'll go ahead and run that. You can see it's cleaning everything. And now I'm back to my base state here with just the zero, constant, and system. So if you want to run your simulation again, sometimes it's nice to kind of just go from the beginning. Let's say that you've changed a bunch of stuff, right? So to basically run the simulation again, I'm going to run block mesh. I'm going to do foam run, okay? And then that runs my simulation again, okay? Okay. All right, so that's OpenFOAM there. So that's basically how you run your case. Let's talk about what I'm asking you to do for the rest of the activity. Okay, so there's four problems for you to do. So problem one is short answer. So just like the rest of the homeworks, these questions here you can answer with just a simple kind of couple sentences. Okay. All right. So all of these can be answered by based on what we did. Okay. Problem two, I want you to refine your mesh. Okay. So remember to refine your mesh. Let me clean again, actually. Okay. So to refine your mesh, you're going to go into the block mesh dictionary file, right? So we go into our systems directory, we go and look at block mesh dict, okay? Right. And then to modify your mesh, you would change this setting right here, okay? So because right now, we're running a simulation with 20 cells in the X direction, 20 cells in the Y direction, okay? So if we wanted to modify this, so let's say that, where is my thing? Oh, okay, so let's say we want to refine our mesh, and so instead of 20 by 20, let's say we want to make a 40 by 40 mesh, okay? So we basically just make that change there. Okay. So this is where the foam clean case kind of comes in handy because you don't want to be overwriting your results. So you go ahead and run block mesh again. Okay. So you can see now that our number of cells here is much higher because now we're 40 by 40. So the number of cells here is 1600 as opposed to 400. Okay. Okay, so I'm not gonna run the simulation again, but if you did foam run, what you're gonna see is that the simulation is gonna take much longer this time because the mesh is much more fine. Okay. Another thing that you'll see, right, just like we kind of mentioned earlier, is that your Courant number is also going to change as well, because Courant number is a function of the grid spacing delta x. Okay. So by refining our mesh, we are basically making delta x smaller, and so that means our CFL number is going to increase. Okay. And so you want to make sure that if you refine your mesh, you want to make sure that your simulation is still stable. Okay, so your Courant number is still less than one. Okay. Okay, so that's problem two. That one's pretty straightforward. That's a pretty easy one to change. Okay. Problem three, I want you to adjust one of the boundary conditions. Okay. So remember to adjust the boundary condition, adjusting the boundary conditions actually is going to take a couple steps. Okay. So first thing you need to do is you're going to need to once again go into block mesh dictionary file here. Okay. Right. And so one thing you're going to have to do is you're going to have to modify this by adding another kind of boundary surface here. Okay. So we can call this moving wall 2. Okay. Right. Because essentially what I want you to do in this part is I want you to add another moving wall. Okay. So let's go ahead and do that. Right. Add in our curly braces here. Okay. So for the moving wall 2, you're going to define this as a wall type as well. So you're going to do type wall, just like up there. Okay. Right, so we're basically just copying the same syntax that we have for moving wall. Okay. Right. Okay, and then you need to define one other collection of vertices here. So let's say that we want to make the right-hand side wall move as well. Okay. So if we go to our geometry up here, right, our right-hand side wall is given by the vertices 2, 6, 5, 1. Okay. And so that is that collection right there. So then you would just add that in here. Okay. So that's 2, 6, 5, 1. Okay. You would then have to delete that from the fixed walls because that's no longer going to be a fixed wall there. Okay. Okay. And then what you would do from there is that you would go inside the zeros folder and modify the U file, right? And then add a boundary condition for moving wall 2 here. Okay. Okay. And then you would kind of copy the same format that we have there, except for moving wall 2, you want the velocity to go either in the positive y direction or the negative y direction. Okay. Okay. You don't have to pick the right wall. I just did that one just because it's the first one that I saw. But I want you to adjust the boundary conditions and then rerun the simulation and see what that looks like. Okay. And by the way, you don't have to choose a velocity of 1 either. So you can pick an even higher velocity or even lower velocity and kind of see how that affects the results. Okay. All right. And then the last thing I want you to do is for problem 4, I want you to change the geometry. Okay. So for this one again also involves you changing the block mesh dictionary file. Okay. But for this one, so to change the geometry, you're actually going to change the locations of some of these vertex points here. Okay. Now, there's a lot of different ways you can change the geometry. I don't want you to go too crazy because otherwise it becomes difficult to apply the boundary conditions. So the only thing I want you to do for this last problem is I want you to adjust either the horizontal length of the box or the vertical length of the box. Okay. So basically, I want you to either make a wide box or a tall box. Okay. And I'll let you guys decide how wide and how tall you want to make it. Okay. So I want you to adjust the geometry, run the measure, run the simulation again, and then see how that affects your results. Okay. Okay, so pretty straightforward. Each of these shouldn't take you too long. I'd say probably problem 3 is probably going to be the most annoying just because you have to kind of make adjustments to the boundaries. But the idea is to give you guys actually practice modifying these text files because it's one thing to kind of watch me do it up here and kind of follow along, but you don't really learn the software. It's just like any software, right? So you don't really learn the software until you actually try to use it yourself without kind of a guided kind of thing, right? So that's kind of the hope with these kind of problems down here. So, but yeah, if you have problems with these, definitely, feel free to send me an email at any time and, I can kind of help you out. Okay. I say these as if they're very simple. So, it is very simple to kind of type up the commands if you know what you're doing. But, I know when you're learning a software for the first time, it is kind of challenging. So, don't be afraid to ask questions, even just as simple as, I forgot how to modify a text file in Linux. That I know that's not even straightforward to do. So, definitely send me emails, come to office hours over the next week, just to make sure you can get this done. Okay. All right, any questions on this before we jump back into the lectures? Okay, all right, so that's OpenFOAM. So yeah, so go ahead and have fun with that. And of course, let me know if you have any issues. Okay, so for the last 30 minutes of class today, I did want to kind of start our next topic because I do want to finish this before we kind of leave for spring. Okay, so let's kind of bring back the iPad here. Go and share my screen. It's ready. Okay, so the last topic that we're going to cover before we go to spring break it's kind of a fitting end to kind of everything that all the theory that we've gone over up until this point in the class, right? Because up until this point in the class, we've mostly been concerning ourselves with finite volume discretization, okay? But in some sense, in a class like CFD, everything that we've done up to this point has been a little bit kind of, maybe not what we're looking for, because we haven't solved a single fluid mechanics equation at all yet. Okay. So the last topic that we're going to cover before spring break is what I call the finite volume formulation of Navier-Stokes. So kind of bringing a lot of things kind of full circle from kind of where we started, right? So the very first lecture, we introduced the Navier-Stokes, and then we didn't really see it again for like 10 weeks, right? So this kind of brings everything kind of full circle back to kind of where we started, right? Okay, so let me start by saying that so far we've been focusing on the finite volume discretization of what we call the general conservation equation. Okay. And so let me go ahead and write that again here just for your reminder. Right? So we had u partial phi partial x plus v partial phi partial y is equal to q, or let's do the diffusion terms first. So let's do k times partial squared phi partial x squared plus partial squared phi partial y squared plus some q, some source term as a function of x and y. Okay. So we've been focusing all of our energy on this particular equation here, which, again, but so here, this is the two-dimensional version of the formula. Okay. So let me kind of remind you what each of these terms here represent. Okay. And so on the one hand, the first that we have here, of course, these are our convection terms because they also have our convection velocities and our first derivatives. Okay. In particular, we're going to make the distinction today. We haven't really made the distinction up until this point, but we call these the linear convection terms. Right? Because there's no nonlinear. So the convection velocity is kind of separate from our conservation quantity phi. Okay. Our next group of terms here, that is the terms here that those are our second derivatives multiplied by k. So these are the diffusion terms. Okay. right? So we spent quite a big deal with that. And so remember, with diffusion, we always discretize them with some kind of central difference or some kind of linear profile for finite volumes. Right? And then our Q, of course, this was our source term. Right? Okay. So basically three main components of this equation that we kind of paid a lot of attention to this. Okay. All right. So this is a good start, right? And so this is, we have to kind of start somewhere with Navier-Stokes. But I would say this is only about half the battle, right? Because the real Navier-Stokes equation has, not only does it have additional terms that we haven't discussed yet, but it also has additional complexity. Right? I know probably not what you want to hear after 2 months of hardcore kind of theory with finite volume and finite differences. We do all that work, we're only halfway there, but that's just the reality of it. Okay, so let's write out the Navier-Stokes equations again. Okay, just so you can kind of see. All right, so Navier-Stokes equations look like this, and so I'm going to write it all out, and then we'll explain the different terms. Okay, so that's our full Navier-Stokes equations, at least in 2 dimensions, and specifically, this is just the x component. Okay. So that's one thing that makes Navier-Stokes a bit more challenging, is that it is a vector equation. And so not only are we solving for just one quantity phi, we're actually solving for all components of velocity, u, v, and if we're in 3D, w as well. Okay. So in Navier-Stokes here, we do see some familiar faces, so let's identify that. Right. So first thing we have here is our convection terms. Right. Right. So Navier-Stokes does have convection. Um, it's actually a big part of Navier-Stokes. But one thing that actually separates it from our conservation equation is that these are nonlinear convection terms. Right? They're nonlinear because you can see, if you look at the first term, we have u multiplied by the first derivative of u. So since we have u times u, that makes it nonlinear. Okay. Same thing for the second term too. So even though it's v, v is also a component of velocity. So we have velocity times velocity, which makes it nonlinear. Okay. Okay, on the right-hand side here, we can see that we have our diffusion term. So this looks extremely similar to our conservation equation. It's just that the symbol, our solution symbol was different. Okay. So there's not really much to comment on there. That kind of behaves exactly as we have done, and we discretize it in the exact same way. Okay. Right, and then we have this term, the gravity term. So gravity is interesting because it is technically an external force, but the way it actually affects our system, it kind of affects our system in the same way as a source, right? So even though G here is gravity, we're gonna say it's the same as like a source because the way we treat it is exactly the same. Okay. So you can make the argument that we've done 3 out of the 5 components of Navier-Stokes. Although for convection, we only did half of that because we did the linear version of convection, but we can say we did half of convection. Right? So the other 2 components here, right? First thing is we have the time derivative, right? So the time derivative here, this is our unsteady term. Right? So discretizing a time derivative actually is, you do have to actually treat it differently. So even though it is just technically a derivative, because it's a derivative in time, the way that we treat it is different. Okay. We're not going to touch that one just yet, That's going to be after spring break. And so there is a collection of methods that we use to discretize the time derivative called time marching sequence. Okay, so that's going to be the theme for the first 3 weeks after spring break. And then we have this guy, kind of the weird, kind of odd one out. Okay. So this term is actually unique to Navier-Stokes, and so it doesn't have kind of a generic name like the other ones. There's no other equation that has this, and so we call this literally we just call it the pressure term. Okay. Because it involves the gradient or the derivative of our pressure. Okay. Or the P with the little tail, with the P with the ponytail that is pressure, and then the one that should be in the denominator that I should have done a better job drawing. That one is rho, which is density. Okay, so it's -1 over the density times the derivative of the pressure. Okay, but together we call that the pressure. Okay. Okay. So what we're going to do today and for the entirety of next week is we're going to take steps to discretizing this equation. Okay. In particular, right, we're going to deal with the most unique part of Navier-Stokes, which is the pressure term. Okay, because there's really no other equation that has a term like this. Okay. And because of that, it's kind of born a lot of really interesting and fascinating kind of theory and methods that are purely specific to just fluids. Okay. Okay. So one thing we are not going to get to in this class, and I did kind of hesitate for this a bit. We are not going to deal with the nonlinearity of the equation. Okay. There are ways to deal with it, and it's not a trivial thing. And so I'm not saying it's not important. It's just there's just no time for it in this class. So we're not going to deal with the nonlinearity, but that is still an issue. But I think the part that I think is more interesting, especially fluid specific, is the pressure term. And what you're going to see is that this term actually brings about some very interesting and very unique challenges to our finite volume discretization. And we need to do some kind of very clever kind of things to discretize that you may not have thought of, right? Even in your wildest dreams. So that's kind of what makes it really, really fascinating here. Okay. Okay. So that's kind of where we're going, kind of the motivation for this set of lecture notes. Any questions on any of this?
Isn't the nonlinearity of the equation make it like you can't solve it with certain assumptions?
You can solve it. It's just that you have to use basically it's called iteration. And so basically you would to solve this numerically, you would have to linearize the equation. So you have to pretend that it's linear and then solve the solution. And then you have to actually go back and correct it again. Which is, not impossible to do, but since we're not doing any coding in this class, we're not actually implementing these methods, I felt like it was a little bit better, more appropriate to go with the pressure term, not that one. Yeah. But nonlinear iteration is not unique to Navier-Stokes, and so there's a lot of equations that have nonlinearity. And so if you take kind of a general numerical methods course, then you'll probably go over methods like Newton-Raphson is a very popular method to deal with nonlinearity in these situations. Yeah. Yes.
There was a second.
Yes. Yeah. Yeah. So I've told a few people that this class is kind of a difficult one because we have just one semester to learn CFD, and there's so much stuff in CFD to learn. If I had my choice, this would be like a 3-class series, and so we take this over 3 semesters. It's just because there's just so much to learn, and that's kind of how I learned it in grad school too. But you can kind of see how difficult this class is, even for you guys to learn. It's because these are graduate topics. I mean, let's not play around. These are hard things to learn. Finite difference, finite volume, pressure coupling. These are things I didn't learn until I was in grad school. But so to learn all that in one semester as undergrads is challenging. And so I think if you guys haven't done so already, give yourself some props because these are not easy topics to learn. So. Okay. All right. So let's get into that pressure discretization. Okay. Now, the first thing that makes the pressure challenging to solve is that the pressure is actually an unknown in our equation. So the pressure is actually something we need to solve. Okay? Right. So we spent this entire time, focusing on solving for, the terms that are in the convection term, the terms that are in the diffusion term, which in this case is the velocity, right? So it's a given that, you're solving a fluids equation, you're going to solve for the velocity. Okay? Right. And remember, velocity is a vector quantity. So there's not only just one component, you have to solve for all three components, x, y, z components. Right? And one thing that we know from math in general is that if you're going to be solving for an unknown, you need at least one equation per unknown that you want to solve. Okay. So for the velocity, let's say in 3D, right? Okay. In 3D, of course, we're going to have three components of velocity, one for each direction. Okay. So U, V, and W. Okay. Right. So that means we need at least three equations that we're going to solve for. And luckily we do have them, right? So remember our Navier-Stokes equations, I told you, is a vector equation. So what I'm showing you here, this is just the x component of Navier-Stokes, but there is, the x, y, and z components of Navier-Stokes. Okay. Right, so that kind of works out very perfectly, right? So we have three components of velocity we need to solve for. Our Navier-Stokes momentum equation has three different equations, and so we can use that to solve for those three unknowns, right? Perfect. But, right, we still need to solve for pressure. Okay. All right, so we need an equation for pressure as well, right? So luckily we do have a fourth equation, right? So not only does Navier-Stokes consist of the momentum equations, we also have our continuity equation as well. So that's conservation of mass. Okay. And so let's go ahead and write that out. So in 3D, okay, our continuity equation has three terms in it. So we have partial u, partial x, plus partial v, partial y, plus partial w, partial z is equal to 0. Okay. Great. So that means that solves our issue, right? So we have four unknowns we need to solve for, and we have four equations, right? But there's a problem, right? Inside this fourth equation, inside this continuity, the one variable that we need to solve for does not even show up in this equation, right? So pressure is absent from the continuity equation. Okay. Right. So we have this fourth equation, but the variable that we need to solve for doesn't even show up, right? So we have kind of a conundrum where we have four unknowns, right? We have three equations in which all the unknowns are basically present in it, and we have a fourth equation where three out of the four variables are present. Okay. And so this presents kind of a really interesting problem we'll illustrate probably mostly on Monday, but we'll start it today, where we have to do some kind of interesting kind of scheme in order to use this fourth equation to solve for pressure. Right? So that's kind of the central question that we're going to answer kind of throughout the next few lectures. How do we use continuity to get an equation for pressure. All right. And so believe it or not, this is still a question that researchers are looking to answer. Or I shouldn't say that. The question is answered. It's just people are trying to come up with new ways and better ways to do it. Because it's not an easy thing. Okay. So, it's the method that I'm going to teach you guys is I would say historically probably the first one that was developed to deal with this issue. It's called the simple method. Okay. And you can tell just by the capitalization that I use there, simple is an acronym. Okay. The acronym is anything but simple, right? So the simple stands for semi, implicit, method, for, the for is silent, pressure, linked, equations. Okay. SIMPLE. Okay. All right. So that is a bunch of words that mean absolutely nothing at this point, but I did want to mention it now, just to kind of show you what it is. And so what essentially we're going to work up towards is, we're going to work up towards, the methodology and the technique for the simple method. Okay. And actually, even though its theory was kind of born and kind of motivated by numerical methods, there's actually some very interesting kind of hand calculations we can actually do with it. And you'll get some more practice with that in homework 4, which will be I'll assign that after OpenFOAM activity 1 is 2. Okay. Okay. All right. So let's start the derivation. Okay. So let's derive the simple method using 1D finite volumes. Okay. All right. So just like we've done up until this point, we start our derivation with 1D finite volumes just to kind of make things simple. Okay. So let me go ahead and draw out our domain here. Okay. So just like before, we have our center cell. So this is going to be cell C. Okay. We have our neighbor to the west. That's W. And our neighbor, well, it's not relevant, but it's hard to just draw 3 cells. Okay. So the neighbor to the west of the west neighbor is WW. Okay. We have a neighbor to the east, that is capital E. And our neighbor 2 spots to the east, that's E. Okay. Okay, so let me go ahead and define some length scales here. So let's say that the length of a cell here, so the width of our center cell, we'll call that delta X. Okay. That's our traditional kind of grid spacing that we've kind of been using up until this point. Okay. Let's also define the distance between the cell center of our center cell, C, and its west neighbor, W, right? So that distance we'll call delta W, or delta XW, excuse me. Okay. And the distance between our cell center C and our east neighbor E, we'll call that delta XE. Right. Right. In most cases, all of those delta X quantities, they are all going to be the same for a uniform grid. But sometimes it's useful to assume that they're different. Okay. So for a uniform grid, we say delta x is equal to delta xw is equal to delta x e. Okay. Right. So for the most part, we are going to assume a uniform grid, but in cases where you have a non-uniform grading, then this theory kind of accounts for it. Okay. Okay. All right. So let's now that we have our domain here. Oh, and by the way, I forgot. The width in the vertical direction, we'll call that delta y. Okay. Normally for 1D problems, we don't worry about that dimension. We only really worry about that for 2D problems, but you'll see that we actually do need it in our derivation. Okay. Okay, so let's take the situation and let's write out our Navier-Stokes equation and our continuity equation in 1D. Because that's going to be our starting point. Okay. Let's actually just start with continuity first. That's the easiest one. So continuity, we have the simple du dx is equal to 0. Okay. So there's no y component velocity, there's no z component, and so our continuity equation just simplifies just du dx is equal to 0. Okay. All right. And so this is a continuity. Okay. All right, and then for the Navier-Stokes, we're going to write it in this form. So we're going to have d dx of, let's see, u times u. Okay, let's do it this way. Let me write this in conservative form. This is rho times u. Okay, so that right there is our convection term. This is equal to d dx of mu times du dx. Right. This here is our diffusion term. Okay. Minus dp dx. Okay. For this last term here, this is our pressure term. Okay. Right, so that's our Navier-Stokes equation. And you can see here that we've neglected the unsteady term and we've also neglected the gravity term, just for simplicity. Okay, so we've neglected the unsteady term just because we haven't gotten there yet. We haven't learned about time stepping. And gravity just is, it's just gravity. There's no need to include it, just to keep things kind of simple. Okay. Okay. So the first thing to notice here is that, just because our situation is so simple, it is very tempting to take the continuity equation and say that, this can plug in here, and so that is 0, so that whole equation goes to 0, right? But we're not going to do that, right? So we are going to actually discretize this whole equation. So I know it's tempting to just plug in 0 and simplify this, but just kind of humor me a little bit, and let's continue with our derivation here. Okay. Okay, so just like we normally do in finite volumes, let's take these expressions here and let's integrate that across our cell C. Okay. All right, so let's actually do momentum first, and so then we'll look at that. So our momentum equation is, we're going to integrate across our cell C of d dx of rho times u dx is equal to integral across our cell C of d dx of mu du dx okay, minus integral of dp dx along our cell C. Okay. Okay. Well, we should have stopped earlier. Okay. I know this is a very awkward place to stop, but we are just about out of time, and I don't if I continue here, it would be another 10, 15 minutes to go. So I apologize kind of stopping at such a weird spot, but when we come back on Monday, we'll pick it up right here, and then we'll kind of carry out our usual kind of finite volume kind of method. So we'll apply divergence theorem. We'll kind of convert our integrals there to surface integrals, right? So we'll do that for convection and diffusion, and we'll kind of highlight a very interesting problem that comes from not only the pressure term, but also the continuity equation as well. That also kind of gives us a very weird result when we do finite volume. Okay. All right, so thank you guys for coming today. I hope you guys enjoyed your first full completed activity in OpenFOAM. Let me know if you have issues with the with doing the last four problems in the OpenFOAM activity. I know it's everyone's first time using kind of Linux for the first time, so issues are bound to come up, so don't be afraid to ask questions. Okay. So hope you guys have a good weekend, and I will see you guys next week.
Yeah.
Hey, Johnny.
I had a question.
Okay.
So do I just have to add my, you gotta wait for a permit?
You should get on the wait list. So definitely get on the wait list. But once you're on the wait list, then you just wait for a comment.
Okay. Oh, okay.
Yeah.
Okay, thank you.
Yeah.
Right. Bring that inside. Or go, if I can like the right size. And then. What should we do? It's 4150. It's like, he said, I'm just.